Hello, welcome to Chapter 6, Normal Distribution. From now on, it will be more serious and everything is continued from Chapter 6 until Chapter 10 because so even if you do not understand up to here, Chapter 5, that is okay, but still not desirable. But if you miss something from Chapter 6, then Chapter 7 will be much more difficult to understand, and so on. It's a restart from this chapter. So let me start. In the previous chapter, I explained that we are going to study parametric distribution families, and we are going to learn two of them. One is the binomial distribution, and the other is the normal distribution. And we are doing the normal distribution. And as you can feel from its name, it's normal. So everything else is abnormal, right? It is the most important distribution, a statistical distribution in any science, including social sciences, like natural sciences and engineering, whatever field, right? So the simply speaking, the reason why is every single random variable we are going to study from now on will be approximated to our normal distribution. It doesn't matter what it is, right? So actually later I will show you even a binary random variable will be approximated to a normal distribution. So that shows this just summarizes the importance of normal distribution. Everything is approximately normal, right? So that you can now feel why it is normal. So any statistics book, any statistics textbook should have a chapter about normal distribution, right? No matter how compact, how concise the textbook is, it must contain normal distribution. Otherwise, it cannot proceed to the main estimation and inference methods. So find you should be able to find a whole chapter dedicated to normal distribution. Again, let me start with a question. Find one random variable that is, again, different from the others. A, amount of tall size coffee, like ons or like milliliter. And B, the time when a bus arrives at in front of me, or when a bus arrives, comes to a full stop at the bus stop. C, weight of a wild caught salmon. D, speed of a car on highway when you use a speed gun, how much it's miles per hour, kilometer per hour. E, number of traffic accidents on a day, right? How many traffic accidents happened in New York State, for example, on say interstate highways. One is different from the others in its nature. The answer is E. There is no correct answer, just my intended answer is E. So E is the number of traffic accidents. It is integers. It is an integer, right? So it can be 0, 1, 2, 3, or can be any natural number, but it cannot be like 1.1 or like 2.7. These numbers are not possible, right? It should be natural or integer by definition, right? But the others are continuous variable, right? It's continuous. That means it can be any number in between any two numbers, right? Even between 0 and 1, there are infinitely many numbers, and even between 1.1 and 1.2, there are also infinitely many numbers possible, right? So all of these are like that. Amount of a tall size coffee, 1.1 ounce is okay, possible. 2.0009 ounce is also possible. Time when a bus arrives, right? If you can measure split seconds or nanosecond of when the bus exactly came to the bus stop, it can be infinitely many possibilities. Weight, speed, right? So all of these are continuous because whenever you think about two different values, there must be another value in between them, right? A little larger than the smaller one, but a little smaller than the larger one. So in that sense, they are continuous. Like in contrast, traffic accidents, if you think about 1 and 2, there is nothing in between them, right? Like yesterday there was one accident, today there are two accidents, and can there be anything in between them? No. 1 and 2, it's just neighboring, like next to each other, so there's nothing in between them. So it's pretty critical and different. You may think it's like, why is that important? Because that's important mathematically. Um, so we are going to call the continuous infinitely many possible outcomes as continuous random variable, because as I said, there are continuously many possible outcomes like next to each other. But the other is called discrete. Integers are discrete. So there are certain increment and there is nothing in between those 2 points. So we call them discrete, and they are pretty important when we handle the probability. So now the reason why is, it's pretty intuitively speaking, continuous random variable has too many possible outcomes. We cannot list them up. Like number of traffic accidents are like can be 0, 1, 2, 3, 4, up to like more, but still you can list them. But think about like bus arrival time or amount of coffee. You cannot list because whenever you write two different numbers, there is another one in between that. And in that way, it does not end. You cannot list them. There are uncountably many infinite possible outcomes. So all our approach does not work. So far, from chapter 1, I analyzed the randomness like using a probability distribution table. So when I say table, that means you have to list possible outcomes, but that is not possible anymore. Like bus arrival time can be like say noon or like a second past noon, or like half second past noon, or like say split second past noon. Anything is possible. It is impossible to list all the possible like outcomes and write down their probabilities. So our approach does not work anymore. Okay, so we are going to change our approach. So to illustrate the problem, let me describe it a little more. Suppose that you are waiting for a bus. The bus is supposed to come at noon, and but like it is random. The arrival time is random, and simply suppose that the bus may arrive 10 minutes earlier or 10 minutes later than noon, right? And so, but it does not deviate more than that. So within the 20-minute window, the bus will arrive with 100%. Okay, that is a probability statement. The bus will arrive between 11:50 and 12:10 with 100%. Okay. Now, what I'm going to assume is, so then what is the probability that the bus arrives between 11:55 and 12:05 within the 10-minute interval? I will assume that that probability is proportional to the length of the time interval, right? So earlier I assumed that I knew that the bus will arrive within 20-minute interval. But now I'm thinking about 10-minute interval. Then how long, what is the probability that the bus arrives within the 10-minute interval? According to my assumption, if the probability is proportional to the time interval, 10-minute interval should contain 50% because the length is half of 100%, right? Right? It is just based on the assumption, right? And then you try this. Same idea, you can extend the same idea to calculate the probability between 11:58 and 12:02. So plus minus 2 minutes. What would be its probability? Okay, it's pretty simple. The answer is 5% because 20-minute window had 100%, which means each minute contains 5%. So then 4 minute should have 20%. Okay, so the answer is 20%. So 4 minute window is 1/5 of the full interval, 20-minute interval. So the probability is also 1/5, like 20%. Okay, so this is reasonable. Of course, it's you may argue if the assumption is correct or not, but anyhow, there is no internal conflict. It is a possible way to define probability. Think about probability. Now then, let's think about this. What is the probability that the bus arrives exactly on time, exactly at noon? So this is tricky. So I think you may realize that the answer should be 0, because for this answer to be 2%, that means you have to have at least like 0.4 minute contains 2%, right? So 4 minute contain 20%. So like you need 0.4 minutes to have 2%, but exactly on time is not 0.2 minute, right? 0.4 minutes. So the answer is 0. The only possible answer is 0. So you can think it like this. Exactly at noon is a moment of time. It is not an interval. Moment is just one point. It's not a line, right? So there is no length. Moment has no length. So the length is 0. That means probability should be 0. Probability is proportional to length. So like if you you can imagine, or the other way, you can think like this. If you believe that the probability exactly at noon is, say, a small probability, then you should be able to calculate the time interval that has the same probability. But a moment is exactly at noon should be just smaller than that much interval. So it should be 0. This is 0. 1 point of time has 0 probability, right? This is true for any continuous random variables. Any continuous random variable has no probability at a point, right? So a tall coffee cannot contain exactly 12 ounces. You cannot drive a car exactly at 60 miles per hour. Or the weight of a salmon cannot be exactly 1 pound. Its probability is 0. Because exactly means 1 point containing no length. This is the problem. Like, as I said, the main problem is that we cannot list all the possible outcomes because there are too many possible outcomes for a continuous random variable, right? So even further problem is there are too many outcomes. So as a result, each of the outcome, even if we could list the outcomes, still the probability of each outcome should be 0. That is a bigger problem. So probability distribution table does not work. Like each outcome has 0 probability. This is mathematically correct statement, right? Any continuous random variable has 0 probability at each point. Each outcome has 0. So we have to change our approach to inequality. instead of thinking about one point, we have to think about something like a probability a tall coffee has less than 12 ounces, or the probability that you drive a car faster than 60 miles per hour, or probability that a wild-caught salmon is between 1 and 2 pounds. So in this case, you can clearly see that it's inequality. Inequality is a line, interval, right? So you can think about length. One point cannot have length, but line, which is a collection of many points, can have a length. So from there, you can think about probability, right? This is very interesting fact. Like it's a mathematical argument, but you will see you can get a better idea based on thinking about point and length, point and line. Okay, so to summarize what I just said, if x is a continuous random variable, at a point, like if you think about probability defined by an equality, it is zero, simply zero, right? So equality does not work. So we have to use inequality to define the probabilities. It's pretty interesting because in the previous chapter, I said inequality is inconvenient to handle, but now it's the other way. Just mathematically, we are not able to handle equality. So we have to use inequality as our basis. And so when you think about inequality, you may think about weak inequality, including like smaller than or equal to, versus strict inequality, smaller than, strictly smaller than. But I don't care because the probability defined by equality is zero, including the endpoint or not, does not change the length, right? So between 0 and 1, including them, versus not including them. Still, they are the same line with the same length. Of course, the endpoints could be included or not, but does not affect the length, so does not affect the probability. Therefore, I don't care about the strength of the inequalities. I may switch between them, right? So inequality and strict and weak inequalities have the same probability implications. Okay, so keep that in mind. Like it can be really counterintuitive to think about one point as zero, but their collection of one point could have positive probability, but this is like the idea of limit in mathematics, like sending a point down to zero, right? So the probability will converge to zero in the end if the line comes down to a point. So that's how we define the probability. Okay. And then here comes the cumulative probability again. So in chapter 3, we learned cumulative probability to define median. And also in the last chapter, I showed you on Excel the formula, binomial formula has another entry about to designate whether it is cumulative or not. The reason why is it's important to study continuous random variables. It's mathematically very important because it characterizes the random variable. That means if two random variables have the same CDF, cumulative distribution function, they are the same random variable. They are the same randomness. And no matter what the random variable is, you should be able to define the CDF. It is unique. So there are many mathematical theorems about the properties of cumulative distribution function, and it is defined by the uppercase F of x. So when you choose a value x, then the function returns probability up to that point, smaller than x or equal to x, right? So, and if you change the entry, the input x, then your output will change. So it is a function. Okay, and we are going to use the CDF as our starting point to describe the randomness of continuous random variable. Okay, so in the next video, I will give you another example to generalize this idea. Actually, the previous example was kind of limited, so I will introduce the general idea with a more general example. See you there. Bye.